Today we have two speakers this morning, 9:30 to 11, so 45 minutes talks each in the plenary session. The two speakers are Bernard Schutz and Richard Bond. Both of these people have been involved with Indian science and also especially with IUCAA. They have been on the scientific advisory committee right from the early stages, from 89 or 90 when IUCAA came up. So very happy to chair this session when both the speakers are there. So let us start with Professor Bernard Schutz. The title of the talk is Gravitational Waves and Astronomy for the 21st Century. And the second talk is by Richard Bond, Probing the Cosmic Theory of the Early and the Late Universe Physics. So, Professor Bernard Schutz.
Thank you, Sanjay. There's been a lot of discussion of gravitational waves at this meeting, appropriately because of the LIGO India project that we hope will be confirmed sometime in the next few months and then greatly contribute to the worldwide effort to detect gravitational waves. There'll be a talk tomorrow by Stan Whitcomb on the current progress, the detectors, the LIGO instruments, and so on that we've been operating now for some years and taking data with for some years. There'll be a panel discussion also tomorrow, led by Sathyaprakash on the same subject. It's my great privilege to introduce the subject. We also had a parallel session, of course, early in the meeting, and there were lots of posters, so I'm sure that a lot of you have had a chance to hear the issues that we're talking about in the gravitational wave field. It's my privilege today to talk about the astronomy we expect to do when we put the advanced detectors into operation in a few years and enlarge the network of advanced detectors by adding LIGO India particularly, and also, as we expect, a detector in Japan. So there's a lot of science to be done by this network. It's all 21st century astronomy, and so that's the title of my talk, and that's where I'm going with it. But first I want to just remind us how long the road has been to get to the present situation, because Joe Weber built the first gravitational wave detector back in the 1960s with a sensitivity, as I put on this slide, which one could generously estimate at 10 to the minus 16, possibly even he was starting around 10 to the minus 14. And in the decade of the 2000s, the big instruments, LIGO and Virgo, reached sensitivities that nominally you could call 10 to the minus 21, which was the first stage goal of the LIGO project. That's a long development cycle. I don't know of any parallel, any other field of astronomy or physics which has had to develop so many, had to improve its sensitivity by so many orders of magnitude over such a long period of time without a single positive detection. Without a single result other than upper limits and of course the scientific and technical excitement of constantly improving our instrumentation. The goal has always been driven by the astronomical return, but that hasn't happened yet. And it's a tribute to the people who've been building these detectors that they've sustained their interest and their enthusiasm, and increased their interest and enthusiasm, and increased the size of the field all the time, while still not returning a single observation yet. Astronomers don't get that. I think this is something that's unique to gravitational waves. We've lived with it for a long time, but I think to most astronomers this is totally mysterious, because X-ray astronomy, for instance, the first sounding rockets that went up even before we had satellites were detecting some extraterrestrial X-ray signals, and radio telescopes, and the CMB was discovered by a communication equipment. It wasn't discovered by a CMB satellite. So you've always had in astronomy development of fields right along. Every new instrument came along, new sensitivity, new sorts of discoveries. We've gone through a succession of new instruments, and we're still waiting for that first discovery, which isn't a surprise because we understand the astrophysics of these systems, and we know we have a long time to wait. But that waiting time is probably going to come to a close in a very short time. So astronomy has advanced enormously in this period of time from the 1960s to the 2000s. The 1960s was an incredible decade of discovery. When you think about that pulsars were discovered in the 60s, QSOs, quasars, SCOX-1, although it wasn't understood, was first observed in the 1960s as cosmic microwave background, and many other things. It was a decade of enormous discovery. It's also a decade in which the first effects of indirect effects of gravitational waves were identified in controlling the orbit of cataclysmic binaries. This was suggested by Faulkner in the 1960s. It was a precursor of what we now see in the binary pulsars, that the orbits are shrinking, but it was in a much more complicated system with lots of gas transfer, so it wasn't really a test of general relativity, but it was the first real application of gravitational waves that I know of, and that occurred in the 1960s. Astronomy knew that the universe was expanding, but didn't know how fast with any precision. You had people favoring a Hubble constant of 40 and people favoring a Hubble constant of 100 or more. So there was a big uncertainty in the parameters of the universe. No black holes were identified. In fact, most astronomers didn't think black holes would exist. It was 1960 was only 5 years after Einstein died, and Einstein thought that black holes didn't exist. So it's not surprising maybe that not very many people believed in the existence of black holes. And of course, no dark energy, as we've heard in this meeting before. Everybody threw out lambda set lambda to 0 conventionally. And of course, we didn't have gamma ray observing by that time. Now, if we go shooting ahead to the decade of 2000s and ask what's in astronomy in this past decade, of course, we know thousands of neutron stars, and they're being studied routinely as pulsars, mainly in the radio, but also in X-ray and gamma ray. Binary pulsars for testing general relativity, much better than the original cataclysmic binaries. Black holes now it's a consensus. We have black holes, and they're known to have masses in the range from a few solar masses up to potentially 10 to the 9 solar masses in the quasars. Jets coming out of black holes and out of neutron star mergers presumably underlie a huge range of phenomena on all scales, from QSOs and AGNs down to gamma ray bursts. And cosmology is precision cosmology. The lambda cold dark matter cosmology has been fantastic at fitting observations, and the observations are highly detailed. So we have cosmology has just undergone an incredible revolution. Now there are three reasons I would give for this change from the 1960s. Technology, technology, and technology. The advances in astronomy have been driven by the advances, the ability of astronomers to bring new technologies, and particularly CCDs and space-based technologies into the field of astronomy. So we're trying to do that last step of technology with our gravitational wave detectors. What were the goals of gravitational wave observing in the 1960s? Supernovae. That's all anybody talked about. That's what Joe Weber was after. A kilohertz burst of gravitational waves from a supernova, hopefully in our galaxy, not too far away, the hope was it was going to excite his bar detectors. What do we think in the years of 2010 and so on? We expect a whole range of gravitational wave sources that people in this room have been talking about on the posters and in the sessions. We expect to identify neutron stars through neutron star mergers and understand much more about the distributions of their masses. We want to study black holes and supermassive black holes in binaries, detailed tests of strong field gravitational, of strong field general relativity by observations of black holes and phenomena near black holes with gravitational waves, searches for gravitational wave pulsars, finding a gravitational wave stochastic background, measuring the universe, measuring parameters like the Hubble parameter and the W parameter, and a whole list of other things. That list there is basically the table of contents for what I'm going to be talking about for the rest of this talk. So there's a huge increase in the amount of astronomy that we're expecting to do. The astronomy goals now are very rich, and that's what's been driving the projects in the last few years. As the astronomers have understood more about the universe has, in a sense, got closer to the gravitational wave projects. What we can do in terms of returning information into astronomy is much more interesting to astronomy today than it was in the 1960s. So I want to talk first about the ground-based detectors and imagine bringing them in, what will happen as they come in stages. So around 2015, according to the present expectations within the LIGO project, the LIGO detectors may start observing, although perhaps not with their full advanced sensitivity. So roughly speaking, I'll just say, what if we have a couple of 10 to the minus 22 detectors in the beginning, and then go up to a network of 5 detectors with that sensitivity? What sorts of things can we expect? So the initial period, we'll expect that LIGO Hanford, LIGO Livingston, and Virgo would come online. Then in a second stage, hopefully not very much delayed beyond that first epoch of the detectors coming online, we'd expect to see LIGO India if we could get approval for that. And if not, then it might be that the second, that detector that would be put in India would also be built at Hanford, so we'd have 2 detectors at Hanford. And hopefully after that, or simultaneously with that on the same time scale, LCGT in Japan, which has an initial sensitivity goal that's more like the initial LIGO goal that it might reach in 2015 and 16, but then it'll bring in cryogenics and other improvements and go to 10 to the minus 22. And so it might be that by around 2020, we could be seeing a full 5 detector network operating. And that's the sort of standard network that I'm going to be talking about in terms of what is the science that we can hope to get to. During this time, the other ground-based detector, GeoHF, which of course is very close to my heart, is operated by my own institute, will and is already doing sensitive observing at frequencies above about 800, maybe 600 hertz. So this sort of kilohertz instrument band, GEO will be able to provide supplementary data to the larger detectors. And of course, because of the importance of astronomy, coincident observing with electromagnetic astronomy is going to be a big feature of what's coming along. We call that multi-messenger astronomy, and we're in the LIGO Virgo collaboration currently talking with many projects and already exchanging triggers where gravitational wave observations trigger an astronomical observation, or an astronomical observation triggers a search in the gravitational wave data. These are the locations, those red dots are the locations of the 5 detectors that I was just talking about. And they form a network. When they operate and exchange data, they form a network. The initial network is those 3, and it's essentially the minimum network that you need for direction finding. You have to have at least 3 detectors in order to get enough information to give from time delays between the detectors to triangulate the location of a source in the sky. And so that's a very important science driver is how many detectors we have. So as soon as we get 3 detectors working, we're able to sort of fully explore the gravitational wave signals that are being detected. The baselines are important because essentially the resolving power of this telescope, this network of detectors, is set by the same criterion as you would for any optical or radio telescope. You look at the size of the aperture, the separations of these detectors, and divide by the wavelength of the gravitational wave. In time units, the distance between Hanford and Livingston is about 10 milliseconds, and the gravitational waves that we're looking at from ground are in the frequency range of best sensitivity around 100 hertz, and that means timescale periods of about 10 milliseconds. And so that's basically one wavelength of the gravitational wave. So that's not a tremendously good baseline for resolving directions. In this initial network, the best baseline is 27 milliseconds, and that's like of order 3 wavelengths. If we can extend and get India involved, then of these 5 detectors, the longest baseline is between Livingston and India, and that's about 38 milliseconds. And that makes, again, an improvement in the sensitivity, in the direction finding. Now, the direction finding, as with any optical telescope, within what's called the point spread function of an optical telescope, you can localize a strong source much more accurately. And that's also true in gravitational waves. The resolving power is not the limit. It doesn't give you the limit. It's the starting point for understanding what angular accuracy you have, but it improves with your signal to noise. The science with the first network, I want to refer to a paper that the Liga-Virgo collaboration published. And in that paper, we estimated the rates of coalescing binaries for neutron stars and black holes, both the physical rates from the astronomical literature and then the detection rates from our understanding of what the detectors can do. For a single detector observing a neutron star in spiral, the range of a detector of the interferometer is about 450 megaparsecs. That was the assumption anyway. And that's what I'll take as a baseline for the full advanced LIGO sensitivity. What I've drawn there in that picture is the antenna pattern of a single interferometer, this famous peanut diagram. I've drawn it as an amplitude pattern, which means it gives the range of the detector, the relative range in different directions. So up the axis, if the detector is in the XY plane, up the Z axis is the best direction for sensitivity, and then the sensitivity falls off in other directions. This is a polarization averaged diagram. The merger rates that were estimated in the paper range from 1 to 4,000 per year per galaxy, per Milky Way equivalent galaxy. The best rate, so the literature, of course, has a lot of uncertainty, but the best rate seems to be about 100 per, no, that's not per year, sorry, I left it out. That's per million years per Milky Way equivalent galaxy. So 1 per 10 to the 4 years in any typical galaxy. That's interestingly, that's significantly higher than we were using as a predictor of performance of these detectors even 10 years ago. So so the astronomy has boosted our expectations. With 3 interferometer, then the detection rate would be the best detection rate, the best estimate would be about 40 per year. It could be as low as 0.4 per year or as high as 1,000 per year, but the best estimate is about 40 per year. And for black holes, the numbers are not very different. And that's because although the volume density of black holes is smaller, you can see them much further away. And the detection rates here are conservative. They're not the ultimate sensitivity that I could have, but they're realistic, taking into account the way we do the data analysis, taking into account that we don't have perfectly Gaussian noise. We have glitches in the detectors that masquerade as signals, and so you have to take care of all of that. The first detections are going to be infrequent. When we first turn these detectors on, it's not like there's going to be a huge cascade of detections, but the first detection will probably be infrequent because we won't have reached the full sensitivity, and if we only have 2 sites in the beginning, we won't even get direction. So the field will start off with in a limited way. But all these numbers assume a threshold on signal noise of 8. So any signal that's detected already has 8 times better position than the resolving power, the raw resolving power of that network. This is the antenna pattern of HL, that is the Hanford and Livingston detector together, and it's drawn realistically with as if you were standing above the Earth, looking down somewhere in the middle of the Atlantic Ocean and a little bit north of the equator, and that bias, that anisotropy, reflects the fact that the 2 detectors, of course, are in North America, which is off to the left as you're standing above the Atlantic Ocean. Now, from the same point of view, if you add in Virgo, and if you put 2 detectors in Hanford, which is what we would have if we didn't have a detector in India, then the antenna pattern gets a lot fatter, and its reach also extends more because there's 2 detectors at Hanford that are adding together. So it gets a bit more round. That's the realistic antenna pattern. So this first net is going to look at neutron star mergers and black hole mergers. We're going to learn things from just comparing the waveforms, even if we don't know the locations of things, about neutron star equation of state, and Shibata is going to be talking about neutron star merger simulations, neutron star black hole simulations. And so we'll get a lot of information even from these very first network of 2 or 3 detectors. There's also a lot of evidence now, and a lot of people believe that gamma ray bursts, a certain class of gamma ray bursts, the short hard gamma ray bursts, are associated with neutron star mergers. What are the implications of that? Well, the beam that comes out, the gamma rays are beamed, and the fraction is probably of order 1% or so. That is the fraction of the sky that's covered by the beam. This is a picture from a simulation by Luciano Rezzola and the numerical relativity group at the Albert Einstein Institute. An MHD simulation in full general relativity of the merger of 2 neutron stars leading to a black hole at the end. And after the black hole is formed and a lot of material has begun to fall into the black hole, this is the pattern of the magnetic field. So this is not the pattern of the density, but just the magnetic field. And you see it's broken up in a very organized way into a toroidal kind of chaotic magnetic field in the disk, but then a very organized poloidal magnetic field pointing up the rotation, the spin axis of the black hole that's been formed, and the angular momentum axis of the disk. It has the potential. That's the sort of skeleton in which we expect then the jet to be emitted. But there isn't enough physics in the simulation to produce the gamma ray jet. But that's where the jet should be going, and that's why one of the strong reasons we believe that there be jets associated with gamma ray bursts associated with neutron star mergers. And so what would happen if we're observing neutron star mergers and we begin to see gamma ray bursts? Well, the initial 40 per year or something may only have of order 1 burst associated with it. So the number of associations between detected gravitational wave signals and bursts won't be very large in the beginning. On the other hand, every neutron star merger of the 40 that we typically expect to observe will lead to a search of a sky error box. You can ask how strong the nearest of those events out of 40 is, just randomly placing them in Euclidean space. You would expect a signal noise of about 27 because our threshold is 8. So the strongest one probably have a signal noise of 27. And for that one, the best error box, the resolving power of this network that I showed you, would be of order a degree. A half a degree is maybe a bit optimistic, that's what the number comes out to be, but it would be of order a degree. And that would mean that you'd have a good chance of finding at least the nearest one, even if you don't have a gamma ray burst for it, localizing it, finding something in the sky associated with the afterglow. So that'll be an interesting follow-up right away from the early detections, the first year or so. Binary mergers are standard sirens, as we well know. Sirens because we use the analogy with sound rather than candles with light. And we can infer the distance to them. And the simple scaling is that if you have the chirp time, if you're observing a binary that changes its frequency, then that is sufficient extra information along with the observed amplitude and the observed frequency to give you the luminosity distance. But of course, there's a scaling factor in front of that. There's that twiddle hides a factor of order 1, and you only know that factor if you know all the geometry of the system. You have to know the location on the sky, you have to know the polarization of the system. So you are not going to be able to infer distances unless you have at least 2 detectors for polarization and a location on the sky, which typically means you need 3 detectors. The chirp time, if you want to compare this with standard candles, basically the chirp time is telling you enough information about the intrinsic luminosity of the system, and of course the observed amplitude of the gravitational wave is the apparent luminosity, and the two go together to give you a distance. For the signal noise ratios we expect with the initial networks, those distances are probably going to be accurate to of order 10%. How are we going to use that? Well, one of them is just we'd like to compare with the astronomer's distance ladder. We'd like to have a burst localized in a galaxy and be able to use the tools that astronomers use in the optical to measure distances and to try to compare those two. In any one case, it'll be only 10% accurate, but averaged over 40 or 50 events per year, we might get some information about, and we hopefully these two distance scales will be compatible. We should also be able to measure the Hubble constant on scales out to about a gigaparsec. There was a poster by Del Pozo about that. And this doesn't require us to identify the galaxies. Even if we don't have identifications of the galaxies, and we just have the gravitational wave signals, we should be able to measure the Hubble constant to only a few percent accuracy with only about 50 events. And so that's already competitive with the values that the Hubble constant is already, the accuracy that the Hubble constant is already known. So that's going to be a very exciting output of the first year or so of observing with at least 3 detectors, and hopefully by that time we might be bringing in more. But there's not just binaries. I've focused on binaries. The search for gravitational wave pulsars, for asymmetric neutron stars producing continuous wave signals, is something that is being worked on very intensively in the LIGO-Virgo collaboration. There were talks by Bruce Allen and Maria Alexandra Papa in the parallel session. It's incredibly challenging signal processing, but as we improve our sensitivity, we're going to keep doing this and hopefully get to the point where we can identify pulsars in gravitational waves. The stochastic background is another goal that people have talked about. The goal set by inflation is very, very weak background in these frequency ranges, and so it's probably out of reach of these detectors, but there may be astrophysical backgrounds, or there may be other kinds of ways of generating fundamental backgrounds other than from slow roll inflation, and so we're going to be doing searches. We're going to look for Weber's supernova explosions, but the simulations of gravitational collapse and associated gravitational wave emission have not been tremendously encouraging. What we do have, however, is the possibility of a coincidence with neutrino detectors, which are monitoring the nearby universe. So something in our local group might well turn up in both Kamiokande, Super Kamiokande, for example, and our gravitational wave detectors. And we'll be looking for things we don't really expect. Cosmic strings may be there or may not be there. They have a characteristic signature so we can filter for them and look for them. The data analysis itself is an incredibly involving task and a rewarding one. There's a lot of science, there's a lot of creativity going into the data analysis for all of these sources. Bruce Allen, in his talk, talked about Einstein at Home, the computing platform that consists of screensavers that are on hundreds of thousands of computers around the world, and it's producing, Bruce, what is it, 100 teraflops continuously? Something like that. 600 teraflops? Unbelievable. That people are donating to us to do our analysis, and we're putting that primarily into the search for gravitational wave pulsars, but it's already been finding radio pulsars and gamma ray pulsars. So the techniques can be applied and are being applied in to electromagnetic data. Now, supposing we can add India and Japan into this network. The top picture there is the one I showed you before. 2 detectors at Hanford, LIGO, and Virgo. That's the antenna pattern. If you take one of those detectors and put it in India, and you add the Japanese detector, the antenna pattern gets a lot rounder. It's much more isotropic. It's not deeper. It doesn't go deeper into space. It just picks up a lot more of the space around us out to a given volume, out to a given depth. Having more detectors also improves the network in another way, because our detectors don't run all the time. They have a duty cycle, and the experience of running detectors so far has been that we might have to live in the beginning with duty cycles of about 80%, although we expect that to improve. When duty cycles are only 80%, it's really useful to have other detectors observing, which are also dropping out sometimes, but at random. And so you have at least 3 detectors observing the sky almost all the time. That improves your detection rate. Then we get the better directions, and we get better data analysis because we can discriminate against these glitches, which are also random local in time events that are in different detectors. And if you have more detectors, then they're not going to turn up and disturb your data analysis nearly as much as they have been up until now. So when you put all of these things together, this extended network would detect at least twice as many events per unit time as the network with just 2 detectors in Hanford and no other detectors other than Livingston and Virgo around the world. And that is partly antenna pattern and partly better data analysis. The data analysis, that's the antenna pattern. The data analysis adds another factor of 2 probably over the other network. And therefore, it's not unreasonable to think that instead of 40 events per year, we might be able to detect upwards of 150 to 200 neutron star mergers per year with this extended network. Now, if you've got that kind of event rate, that qualitatively changes the kind of science that you can expect to do. We would expect to pin down the neutron star mass function. We would be able to, from repeatedly looking at different merger signals, begin to unravel the signal from the early stages of mergers before shocks come in. There's 2 kinds of equations of state for neutron stars. There's the hot equation of state after they've shocked, and that's the equation of state also that is relevant when neutron stars are being formed inside supernova cores. But also there's the cold equation of state, which is what governs the typical neutron star pulsar. The cold equation of state, if you can unravel the gravitational wave signal before shocking occurs, as the 2 stars start to merge together, then you get information about the cold equation of state. Then we also should be able to understand not just the equation of state of these neutron stars, but there are some things about their interior structure, and they have fascinating physics inside with superfluidity, superconductivity, maybe very strong buried magnetic fields, and so on. Lots of coincidences with gamma ray bursts, if short hard gamma ray bursts are associated with neutron star mergers, because the gamma ray beaming is along the axis, and that's also the direction of strongest radiation from of gravitational radiation from a binary merger. There's a happy coincidence. So the number of events that we expect to see in coincidence with gamma ray bursts is about 3 times larger than random because of that added sensitivity, the added strength of the gravitational radiation when the beam is being toward us. But if we see a gamma ray burst, we also should, is it all right? That's the amount of time I have? Oh, I should get faster. We should see 50%, we should be able to lower our threshold for gravitational wave detection. So we might get actually a lot more coincidences between gravitational wave detectors and gamma ray bursts. Well, I'm going to skip over the other consequences of that science, and I want to say a few more things about it, but realistically we're not going to get money for that until we first detect gravitational waves. It's an underground telescope with lots of new technologies, very, very challenging. We would like to see this happen at least in 2 places, let's say North America and Europe, and probably observing should still involve the older instruments, the current advanced LIGO instruments. And you can do things, this is, I'm sorry the way this came out, this is meant to be a comparison of, let's see, what you can do with neutron star mergers in terms of measuring the Hubble constant out to distances of redshift of about 2, the green is Bob Kirshner's supernovae, and the red is what we expect we would do with a 3rd generation gravitational wave detector. So they're competitive, and it would be a big contribution to studies of the universe, and also studies of the early evolution of black holes and neutron stars. So I'll skip over that. I do want to mention that we expect to be doing pulsar timing studies at very low frequencies of nanohertz. There's 3 collaborations around the world. Australia, USA, and Europe have their own collaborations, and they're beginning to collaborate with one another. And they're hopeful of reaching sensitivities at least able to see some sort of stochastic superposition of radiation from massive binaries by the end of this current decade. And maybe we'll be able to study individual signals too. I don't want to finish the talk before talking about what's going on in space, and I'm sure a lot of you are wondering what's happening with the LISA project as well. The motivation is to get away from the gravitationally noisy space, just as you have to do that in astronomy to get above the atmosphere. You have to get well away from the Earth in order to be able to observe below about 1 hertz in gravitational waves. LISA has long been the flagship project as a collaboration between ESA and NASA, but NASA had to withdraw because of funding problems. And so I'm going to skip over what we knew about LISA. It's been studied to great detail, and we're building in Europe, we're building LISA Pathfinder for launch in a couple of years. Hardware already exists. Most of it has already been tested and is in mothballs. It's essentially ready to go, waiting for the launch. So we understand how to build this technology, and we just need to get the project together and the approval from Europe to do a Europe-only LISA project, which we're calling ELISA, and which the European Space Agency is calling NGO, the New Gravitational Wave Observatory. So we don't even agree yet on what the name of this thing should be. LISA, of course, has had high priorities in every review that it's had. NASA dropped out, but we now have redesigned it using resources available only in Europe, and we've been able to get sufficient resources to do what is effectively about 80% of the original LISA mission. That is to fund about that would be about 80% of what would cost Europe to do the full LISA mission. So Losing NASA hasn't been a disaster. We've had the descope, but we haven't had catastrophically the descope. We've just been able to reuse LISA Pathfinder technologies and change a few things. The most important thing, the most important two changes is we had to shorten the length of the arms to 1 million kilometers, and we've changed to just 2 arms instead of 3, just 1 interferometer signal instead of 3 interferometer signals, and that affects the science, but not in a way that makes it totally uninteresting. If this was the first mission to be proposed, I think we would all be extremely excited about it. I want to tell you just a little bit about ELISA. I should say we don't really know what the selection procedure is within ELISA yet. Those of you who remember the LISA sensitivity curve will remember that it's shifted relative to the red curve a little bit to the left and a little bit down. Down means better sensitivity, left means lower frequencies. We're now at higher frequencies, a bit higher because we have shorter arms, and we've lost a little bit of sensitivity, but it's still, there's a huge amount of science that's going to come out, and we still do a lot of white dwarf binaries, identify thousands and thousands of white dwarf binaries in our galaxy, tens to hundreds of extreme mass ratio events in the galaxy. There are mergers of black holes, and looking at the star clusters in the centers of galaxies and so on. All of those things are going to be possible with ELISA. Very good measurements, high precision measurements of masses and spins of black holes, of distances to black holes out to redshifts of order 1 with 4% accuracy. That's an extraordinary ability for a single object to measure distances, and lots of relativity questions. Particularly, I want to show you one. The black hole science is just so exciting. Kip talked about. Kip showed you one of these simulations, which I'm going to. I hope it's going to come up. Where is it? There it is. This is the RIT simulation by Manuela Campanelli and her group of the 2 black holes bobbing up and down, and then after the merger shooting off with a very high speed in one direction. That's the signals from this is the kind of thing that we want to be able to study in great detail, and we should be able to compare every phase of an observed merger, because these are signals that are really huge signals. You don't even have to filter the data stream in order to be able to see them. The extreme mass ratio in spiral, where there's a smaller black hole, a 10 solar mass black hole, orbiting around a massive black hole and finally going in, is also really interesting from the point of view of general relativity, because the mass ratio is so strong, is so extreme, the radiation reaction effects are relatively much weaker, and it takes a much longer time for that small black hole to fall in. I want to show you a simulation by Steve Drasko. You see the orbit of the small black hole. The mass ratio here is about 10 to the 5. The central black hole is that larger circle in the middle. It's a curved black hole. So there's all sorts of frame dragging effects that affect the orbit. The orbit is looking really, really complex. You see the waveform at the bottom, and you see how irregular the waveform is. And what you're listening to is the real waveform. This whole thing is just speeded up by that was the most important part, because that's the proof. The fact that it stopped so quickly is the proof that there was a horizon there. If it was some sort of fluffy boson star or something in the middle, it would still continue. The signal would still continue. The fact that it cuts off bang like that is going to be our best proof of all that horizons really are horizons, that black holes really have that. So I'll stop there.
Yeah, okay. Lecture, current review, not only living but current.
Thank you.
Any questions?
Slide on how the Einstein telescope can help us determine the equation of state, the dark energy equation of state parameter W. Now, unlike what you said about the Hubble parameter, in this case, we'll need to localize the host galaxy to get the redshift. So are you assuming that there will be multiple Einstein telescope sites that will be able to localize it?
So, yeah, so I think I showed that in, primarily with respect to the third generation, the Einstein telescope, yeah. And I was assuming that we would have at least 2 sites and that we would have polarization information from these triangular detectors. So there wasn't enough time to go into the technology, but that we would have the ability to localize. But at the same time, is Satya here? I don't know if it's true that we have to have localizations to get W.
That particular one was the work of Wenzhou et al. And they were using binary neutron stars mostly. And if you can get gamma ray counterparts, then you don't need to absolutely, it's not absolutely essential, because you can see up to redshift of 2. If you use binary black holes, again, in principle, you don't need localization. If you can get many, many events with poor localizations, you should be able to, I mean, I'm not saying no localization, but even with poor localization, you should be able to get from statistical analysis, you should be able to get the W and WA.
Merger of 2 black holes in which the resultant black hole moves off in one particular direction. So 2 related questions. One is, what is typical velocity of this? And the related question is that if you instead of black holes, if you take neutron stars, no, could this kind of thing have some implication on the peculiar pulsar velocities?
That particular thing isn't the peculiar velocities of the pulsars, I think. That will come from a hydrodynamic asymmetry. It's a similar effect, but it would be in the hydrodynamic momentum release and the asymmetry of the hydrodynamics. But the typical velocities are of the order of a few hundred kilometers per second. What that simulation showed was a velocity of 2,000 or more kilometers per second. And to get that, you have to have a very special initial geometry, initial arrangement of spins that are strong, but also in the equator of the in spiral. So if you arrange things right, you can get it very, very strong. And the purpose of that simulation was to explore how strong the effect can be. But typically with random spins, it's a couple of hundred kilometers per second.
Okay, let's start this.